Okay, so part three in the secrets of the periodic table. And in this section, we're going to talk about bonds and bonding. And if you remember our recap from the part two video, the recap is that the metals are in this left tower over here, these two columns, and they tend to lose electrons, and which makes turns them into a positive ion. Remember, an ion is an element that has gained or lost electrons, and so they end up having a charge. Most normally in just a regular element has no charge, but if they gain or lose electrons, they're going to end up having a charge. So the metals on the left two columns, they're going to end up losing electrons, which gives them a positive charge, and they become a positive ion. And how many electrons do they lose? Well, it's right here in the table, which is part of the secrets of the periodic table. In column one, they're going to lose one electron, which makes it a plus one charge. In column two, they're going to lose two electrons, which will give them a plus two charge. Over here in the right column, or in the right tower, this big square over here, these are nonmetals, and nonmetals tend to gain electrons, which makes them negative because if you have an imbalance of electrons and too many electrons, since electrons are negative, that's going to make the ion negative. So they're going to turn into a negative ion. So how do we know how many electrons each of these elements in this right block will gain if they turn into an ion? Well, here is column 8, which is the very last column in the table, and you count backwards from that column. And however many columns backwards from that very last column there are, that is how many electrons these nonmetals are going to gain. So I have here, for instance, carbon. We start at column 8 and we count back 1, 2, 3, 4 is carbon. So carbon will gain 4 electrons and end up with a negative 4 charge. So that's just to recap our part 2 segment that we just did. And remember, these rules apply to the entire column. So with carbon, the negative 4 charge that it could get by gaining 4 electrons, that also applies to everything down here. Everything in this carbon column is going to have that same number. It's going to gain 4 electrons and have a negative 4 charge. Over here on the left, everything in the first column is going to lose 1 electron and have a positive 1 charge. Everything in column 2 is going to lose 2 electrons and have a 2 positive charge. And that's when they turn into ions, though. Now, just normally, they don't have any charge, but it's the ionic form is when they gain or lose electrons and turn into an element that has a charge to it. Now, what does this mean to you and me? What that means is that when these two columns over here, any element in these two columns over here, end up with a positive charge, when they're ions, they'll have a positive charge. And everything over here in this block, when they're ions, they're going to have a negative charge. So what does that mean to you and me? Well, this is part of ionic bonding. And if you remember, there are two main types of bonds, ionic bonding and covalent bonding. Well, since we've been talking about ions right now with the elements having a charge, right now we're just going to go into ionic bonding, and then after that we're going to cover covalent bonding, and then I'll show you the difference, or you should be able to see the difference. So right now for ionic bonding, okay, so first of all, let's take, say, sodium. This Na stands for sodium, and that is in column 1. So if sodium turns into an ion, since it's in column 1, that means it's only going to lose 1 electron, and which gives it a positive 1 charge. And then let's take a look over here at, say, chlorine. Chlorine's right here. If you count backwards from the last column, from column 8, 1. We just skipped back 1 column from column 8, so that means chlorine is going to gain 1 electron and have a 1 negative charge to it. So if you bring the sodium, which is missing an electron, and it's walking around, oh, I missed my electron, I don't have enough electrons. So it's looking for an electron to make it complete. Because remember, everything in chemistry happens so everything can go back to balance. So the sodium, since it's an ion and it's plus 1 charge, missing an electron, it's going to go walking around trying to find a new electron to take the place of the old one that it lost. And then this chlorine has too many electrons, and so it has that negative 1 charge. Chlorine's walking around going, will somebody take this extra electron off my hands, please? This is too much. My hands are full. I have too many electrons. So if you notice, this sodium has plus 1 charge, this chlorine has a negative 1 charge, and since sodium is looking for an extra electron or another electron to make it complete, and chlorine's looking to unload an electron to make it complete, these two can come together and fall in love because they have something that each of them needs. Sodium needs to get an extra electron, and chlorine needs to get rid of an electron. So they can bond together, and here's where let's just draw this little vacancy space where the electron is supposed to go, but sodium lost it. And for chlorine, let's just draw this dot for the extra electron that chlorine picked up, and they're trying to get rid of it. So they can go ahead and form this bond between where there should be an electron for sodium and there's not, and where there's an extra electron for chlorine that chlorine's trying to get rid of. And so they're going to share that extra electron, which gets them bonded together, so they can both be complete. So now if we have a sodium ion and a chlorine ion together, they're sharing that electron. So sodium now has all of its electrons it needs, so it doesn't have a charge anymore. And chlorine has dumped off its extra electron to the sodium, so chlorine doesn't have a charge anymore because everything in chemistry happens to get back to balance in order to get back to balance. So now we have sodium chloride. And so this is not going to have a charge because since chlorine gave sodium its extra electron, now sodium's all good, chlorine's all good, everybody's happy, everybody has no charge as long as they stay together in that ionic bond. And I have more videos on ionic bonding that goes more into detail about it. So you want to check those out if you're still foggy on ionic bonds. But I wanted to show you what these charges and that you can find out on the periodic table, what that has to do with what you're doing in your chemistry class. Now, what if we have lithium? We're going to do lithium right now. And lithium, again, is in column 1. So if it turns into an ion, it loses an electron and it gets a positive charge, just 1, because since it's in column number 1, it's going to have charge of 1 because it's going to lose 1 electron. So whatever that column number is, that dictates how many electrons and what the charge is. And then over here on the right, let's say, for instance, oxygen. Oxygen is 1, 2 columns back from the end. So that means oxygen is going to gain 2 extra electrons, which is going to give it a -2 charge. So what do we do when we have a lithium with 1 positive charge and an oxygen with 2 negative charges? How does that work? Because as I said, everything in chemistry, these bonds are happening so they can all get back to normal and everybody can have a 0 charge. But that's not going to work this time because lithium only has a +1 charge. It only needs 1 electron. And oxygen has a -2 charge. It has 2 extra electrons. So if we have lithium with 1 electron and oxygen with -2 electrons, let's just draw our little space where lithium needs to put an electron. It's missing that electron. And let's put 2 dots for oxygen's extra electrons. We'll do 1 there and 1 there. So these guys can kind of fall in love a little bit, but lithium only needs 1 electron, and oxygen has 2 extra electrons it needs to get rid of. So if we bond lithium, the ion version of lithium, to the ion version of oxygen, that's great and all. That'll get rid of lithium's charge, so lithium will just have a 0 charge because it got its electron back. But oxygen is still going to have that 1 extra electron it hasn't taken care of yet. So we got to put another lithium or another element or whatever. Doesn't have to be lithium, but now we're going to have to put another lithium over on the other side here that has that +1 charge. We have to get another ion of lithium that needs an electron. So those two can bond together. And now 2 lithiums have now returned back to normal. They don't have a charge. And the oxygen has now gotten rid of its 2 extra electrons. So we're going to have a bond. We're going to have a lithium and an oxygen and another lithium bond together like this. And so you're going to write it lithium and then with the little tiny number 2 saying that there's 2 lithiums and 1 oxygen. And that would be dilithium oxide. So you have to match up the number of charges together when you're bonding the elements. And if the elements you're using have 2 different kinds of charges, then you need to use more than one of those elements. In this case, we use 2 lithiums and 1 oxygen. So here is where your math skills are going to come into play. And don't worry, I know I say math and half of you grab your heart and have an anxiety attack. It's basic math. It's not anything, crazy. It's adding, subtracting, multiplying, dividing. That's it. Chemistry does not have that difficult of a math background. You just have to know your basics, though. So if you're having problems with your basics, go and see my other math videos on basic math. I have a whole playlist, and you're always welcome to comment on the video and ask a question. No question is dumb. There is no dumb question. There are only dumb answers. There are no dumb questions. So please feel free to contact me if you need more clarification on this. I'm not just some talking voice that just puts these out here and doesn't care about the feedback or doesn't care that you get it or not. I really do. So give me a message if you need any more help with this. But so let's say it's not as easy as just doing 2 lithiums and 1 oxygen because lithium has a +1. So you have to match that with the oxygen, which is -2. So if you take this +1 times 2, you're going to get a +2, and that's going to match the oxygen. So what I mean by that is, let's do another example. and I can show you. Okay, so let's say, okay, let's say we have magnesium. Here's magnesium over on the left-hand side in the metals, and magnesium is in column 2, right? So what does that mean in the secrets of the periodic table?
Join me at the Taylor Swift decoder cam. Okay, let's see.
What does that mean if magnesium is in column 2? Well, that means if magnesium becomes an ion, its ion form loses 2 electrons, and that means it ends up with a positive 2 charge, right? Just like the lithium we just did that had a positive 1 charge because it lost 1 electron. But now we're in column 2, so magnesium, since we're in column 2, magnesium loses 2 electrons. That means it has a positive 2 charge. See, 2 and 2 and 2 and 2. It all matches up to the column number here, this 2A. Okay, so what if we have magnesium, the magnesium ion, which is plus 2, and we have, let's see, I don't even know if this is a real thing, but I'm just doing this for the math's sake. So let's say we have nitrogen over here. So now how do we figure out if nitrogen turns into an ion? How do we know how many electrons that this nitrogen gains? Well, we count backwards from this last column 8. So 1 column, 2 columns, 3 columns. So that's 3 columns back from the column 8 is nitrogen. So that means if nitrogen is turned into an ion, that means it gains 3 electrons. And since electrons are negative, that means nitrogen is going to have a negative 3 charge to it. So over here, magnesium, the magnesium ion has a positive 2 charge to it. And over here on the right side, the nitrogen has a negative 3 charge to it. So what are we going to do with that? So as I said before, magnesium ion with a positive 2 charge, and we have a nitrogen ion with a negative 3 charge. So how are we going to bring these guys together so their charges can cancel each other out and everybody can go back to 0 and be happy? Well, that's where multiplication comes in, because if we have, let's draw it out so we can look at this and see what it looks like. Okay, so here's magnesium, and here's the space where they're missing the first electron, electron number 1, okay? And here's the space where they're missing electron number 2, which is why they have a positive 2 charge. They're missing 2 electrons, okay? And let's draw this out. Here's nitrogen, and nitrogen has 3 extra electrons. So here's 1 extra electron, and here's 2 extra electrons, and here's 3 extra electrons, and that's why it has a negative 3 charge. All right, now if we bring these together, as you can see, we could bond magnesium and nitrogen. So nitrogen can give magnesium 1 extra electron up here, and nitrogen can give magnesium 1 extra electron right there. So magnesium would be good. Magnesium would have a 0 charge. It would be totally good with nitrogen, but nitrogen would still have this extra electron over here that it needs to be dealt with. Okay, so what we can do is we can have a different element that only needs um, 1 extra electron. Like remember lithium that we just did? Lithium's in the first column. And let's go back and look at lithium. See, lithium's in the first column, column number 1. So that means lithium is only going to lose 1 electron and therefore has 1 positive charge. So we can use lithium and connect these together. So nitrogen has now given its 3rd extra electron over to lithium. So lithium is good. It doesn't have a charge anymore. So we would get magnesium and nitrogen and lithium all bonded together. And that would be good. That would be fine because that would bring it back to 0. And actually, you would write this just like you would write on the periodic table from left to right. So lithium is the leftmost, and then magnesium, and then nitrogen. You would just write it left to right on the periodic table. If you see here, lithium from left to right, and then magnesium, and then nitrogen. So you would just write it out from left to right. Usually that's what you do. Sometimes you break the rules and you write it some other way, but I just want you to get used to seeing it both ways. It's the same thing. So if we have lithium, magnesium, and nitrogen, um, that's going to be fine. But what if we can't use lithium? What if the only 2 elements we have are the magnesium ions and the nitrogen ions? So let's get rid of this lithium stuff. What if we can't use lithium? What are we going to do? Well, you're going to have to or you're going to have to use more than one of each element, more than one of both elements. And the easiest way to calculate this is just a shortcut. It might actually be shorter if you do it a different way in some instances, but this is just kind of a shortcut. If you take this 2 charge, this plus 2 charge, and this negative 3 charge, and you multiply them together, And you might recognize this from fractions when you were doing fractions. And you're welcome to check out my videos on fractions if that doesn't ring a bell or if you need help in your math class as well. But if you multiply these together, 2 times 3 is 6. So what we want to do is we want to fulfill enough magnesium ions that take up 6 positives, and we want to use enough nitrogen ions that take up 6 negative electrons. So if we have magnesium, and magnesium, usually the magnesium ion is a positive 2. Well, to get to a positive 6, we need to take that times 3. So there's 3 magnesium ions if you want to have a positive 6 charge. Does that make sense? Now let's look at nitrogen. Nitrogen usually has a negative 3 charge, but we need to get up to 6. So if you take that negative 3 times 2, that's going to give you a negative 6. So this times 2, that means we want to have 2 nitrogen ions, which is going to give us a total of negative 6. Because each nitrogen, we have a nitrogen with a negative 3, and if we have another nitrogen with a negative 3, that's 2 nitrogens, then that means negative 3 plus negative 3 is negative 6. So that's how I got that. So now we can take these 3 magnesiums. So magnesium needs 2 electrons, but there's 3 of them. So each magnesium needs 2 electrons, and there's 3 magnesiums. So now if we have 2 nitrogens, and each nitrogen has 3 extra electrons that they're trying to get rid of. Those right here. Okay, so we have 3 magnesiums for a total of 6. They need 6 electrons. They've lost 6 electrons. And we have 2 nitrogens, and they have 6 extra electrons. Then we can take these and bond them together. Nitrogen can give this extra electron to where magnesium needs 1. Nitrogen can give this extra electron to where magnesium needs 1. Nitrogen can give the second magnesium its extra electron. And then the second nitrogen can give an extra electron to the second magnesium. And then the last 2. So you see how they all tie together. So now we have enough for nitrogen to donate all of its extra electrons that it doesn't need over to the 3 magnesiums that do need electrons. So now we're happy. And you would write that, the magnesium, with a little 3 after it to say that there's 3 magnesiums, and the nitrogen with a little 2 after it to say there's 2 nitrogens. And so now everybody's happy. Everybody has the electrons that they need. Nobody has any extra electrons that they don't need. It's back to balance. There's no charge anymore. And that is an ionic bond. And that's how you calculate how many of each element you need necessary in that bond. Okay, so now we're going to get into covalent bonds. Covalent bonds, which are completely different than ionic bonds. Because covalent bonds are not about ions, not about ions. These are normal elements we're talking about with no charge. So we're not talking about elements that have lost or gained electrons, and so now they have a charge +3 or -2 or whatever. We're not talking about those. We're not talking about ions, because those are ions. We're talking about just regular old elements that have no charge to them. They have the correct amount of electrons to match up with their protons in their nucleus. And it is a completely different type of bond. And here's the thing. It's only between nonmetals. So covalent bonds, we're only talking about like a third of the periodic table. You're not doing this with all of the elements on the periodic table. You're doing this with just the nonmetals over here on the periodic table. Oh, and also hydrogen. Because remember, I told you hydrogen kind of is a rule breaker. It's kind of a rogue element. And a lot of times hydrogen belongs over here next to helium right here. So hydrogen can do this too. So we're just going to, for all practical purposes, for covalent bonds, go ahead and consider hydrogen over here with the nonmetals, okay? So the valence shells, and remember this is from part 1 and part 2 of this series. So if you need to go back and refresh real quick, you can just go do that and come back. But the valence shells, the outermost shells of the orbitals, the electron orbitals, they only can have 1 through 8 electrons. You cannot have 9 electrons in your valence shell. You can only have 8 electrons. But they always want a full set of 8 electrons. So like carbon, if you see carbon here, carbon only has 4, 1, 2, 3, 4 electrons in its valence shell, but it always dreams about winning the lottery and having 8 electrons in its valence shell. Okay, same with oxygen. Oxygen has 1, 2, 3, four, five, six electrons in its valence shell. But it always dreams about winning the lottery and getting a whole eight to fill it up. So it has a full valence shell full of electrons as much as possible because everybody's greedy. So carbon has four, oxygen has six, but they always want eight electrons. So covalent bonding is all about elements seeking each other out so they can share each other's valence electrons so they can technically say that they have a full eight in their valence shell, not their normal number, like oxygen was six. But first, before we get into all of that with covalence, how do we tell how many valence electrons each element has? How do I know that carbon only has four electrons in its valence shell? How do I know that oxygen only has six electrons in its valence shell? Well, let's go back to the secrets of the periodic table.
Join me at the Taylor Swift decoder cam. Okay, let's see.
Now remember how we have these columns numbered up here in group A for the nonmetals. This is column 3, this is column 4, this is column 5, column 6, column 7, and column 8. So easy peasy. How do you know how many electrons are in the valence shell of any of these nonmetal elements? It's the column number. So carbon is in column number 4, so it has 4 because column 4. And that's carbon right here. Oxygen is right here. Oxygen is in column 6. So oxygen, 6 valence electrons because it's in column 6. And it's as easy as that. No trickery to it. Whatever column it's in, that's how many valence electrons it has. Now, for this next part, you're probably going to want to brush up on drawing your Lewis dot structures. Um, and I also have videos for those if you want to go and check out those videos because you need to understand Lewis dot structures. Otherwise, what I'm drawing is just going to look like a whole bunch of crazy dots, and I'm going to look like a crazy person. So if you know a little bit, even if you know just a little bit about Lewis dot structures, that'll help. So let's concentrate on these three um, atoms of elements up in the upper left-hand corner, and we're going to do that, and then we're going to save this one for later. So let's first take oxygen up here in the center between these two other atoms. And we need to know how many electrons are in oxygen's valence shell. Now, we're not going to worry about showing the electrons on the inside orbitals. We're only concerned with the outermost orbital, the valence shell, which I've highlighted here in green. So how many electrons are normally in the valence shell of oxygen? Well, to know that is part of the secrets of the periodic table. And as we went over before, whatever column the element is in group A for the nonmetals, that is how many electrons are in their valence shell. So oxygen is in column 6. So we're going to make 6 electrons. 1, 2, 3, 4, 5, and 6. So this is how many electrons oxygen normally has in its valence shell. But as I said before, it really wants to have 8, not 6, because everybody wants to be like the end column, column 8, who already has 8 electrons in their valence shells. So in order for oxygen to get 8 electrons in its valence shell, it needs to bond with neighboring atoms and who are able to share their electrons with oxygen. So let's look at this F down here. And how many electrons are in fluorine's valence shell? Well, let's go back to the periodic table. And here is fluorine right next to oxygen on the periodic table. And fluorine is in column 7. So that means fluorine has 7 electrons in its valence shell. So let's draw 7. 1, 2, 3, 4, 5, 6, 7. So if we look at fluorine and we look at oxygen, if you notice, oxygen needs 2 more electrons in its valence shell to get 8. And if you look at fluorine's valence shell, fluorine already has 7, so it only needs 1 more electron to get 8. So fluorine can share one of its electrons and bond it with one of oxygen's electrons, creating a bond. And since these are now bonded together, these two electrons, one from fluorine and one from oxygen, then now we can count that oxygen electron that fluorine's bonded to for fluorine's 8th electron. So now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in fluorine's valence shell. But how many do we have in oxygen? Has oxygen gotten 8 yet? Let's see. So oxygen's electrons would count like 1, 2, 3, 4, 5, 6, 7. So now oxygen has 7 electrons in its valence shell. So we're getting closer, but it still needs one more electron in order to get to its goal of having 8 electrons. So it needs to also bond to another atom floating around close by. In this case, it's chlorine. And how many electrons does chlorine have in its valence shell? Well, let's go back to the periodic table and find chlorine. And chlorine is just right underneath fluorine. So it's still in that same row or that same column of number 7, group A7, because it's in the same column as F, as fluorine. So we know it's going to have the same amount of valence electrons that fluorine did, which is 7. So let's draw them up here. 1, 2, 3, 4, 5, 6, 7. So see now chlorine has an electron missing in order for it to get to 8 because it only has 7. And the oxygen is missing an electron in order for it to get to 8 because it only has 7. So we're going to bond these two electrons together and thereby bonding the atoms together. So now we can count both of these electrons in this bond for both oxygen and chlorine. You can share it. They're sharing that's covalent, always means cooperation is how I remember it. So let's look at chlorine first. Chlorine's electrons now, counting the two electrons from the bond, are 1, 2, 3, 4, 5, 6, 7, and 8. So yay, chlorine has gotten its 8 electrons. And what about oxygen? Oxygen would be 1, 2, 3, 4, 5, 6, and then don't forget about this one over here with fluorine, 7, 8. Because each bond is worth 2 electrons. And I got that written over here too. Each bond is worth 2 electrons. So if an atom is bonded to another atom, it gets to count that bond amongst its valence electrons. So you count 2 electrons. Now let's look at these oxygens down here in the lower right corner of the screen. So we've already established that oxygen has 6 valence electrons normally. 1, 2, 3, 4, 5, 6. And here it is again. 1, 2, 3, 4, 5, 6. So oxygen is going to need, since it only has 6 electrons in its valence shell and it wants 8, it's going to need 2 more electrons, right? So between these two oxygen atoms, we're going to take one of the electrons from the left oxygen atom and bond it with one of the electrons from the right oxygen atom, and there's a bond right there. So that gives us one more electron. So now oxygen has 7 electrons, but it needs 8, right? But look, we have an extra electron on each valence shell that we can also bond to each other. So we're going to bond this electron to this electron, and really this moves up a lot closer. So you're going to have the electron here bonded with the electron here. And so this is what you would call a double bond. This is how you get a double bond. So see, there's 2 bonds there right next to each other. So 2 oxygen atoms connected together would look like this. So when we're doing this, I showed you we went to the periodic table and we looked up oxygen and we looked at the column it was in, and that told us how many electrons it does have in its valence shell. So in order to find out how many electrons it needs to get to 8, you just count backwards from column 8. So 1, 2. So we know oxygen is going to need to form 2 bonds so it can get those 2 extra electrons in order to get 8 in its valence shell. And we did fluorine also, 1. So fluorine is only 1 behind column 8, so fluorine is only going to make 1 bond. And same with chlorine beneath it. And as you can see, if we go back to the work that we just did, see fluorine only made 1 bond, and chlorine only made 1 bond. But oxygen made 2 bonds. And that's what we're looking at when we look at the periodic table and we count backwards from column 8. Fluorine and chlorine both made 1 bond because they're only 1 away from the 8. But oxygen is 2 columns away from column 8. And so that means it's going to need 2 bonds in order to get its 8 valence electrons in its valence shell. So all you do is you count backwards from column 8, and that will tell you how many bonds that element makes. So let's try these. How many covalent bonds can oxygen make? Well, that's an easy one because we've just been working with oxygen. So we go to column 8 and we count backwards. 1, 2 to oxygen. So oxygen can make 2 bonds in order to get 8 valence electrons in its valence shell. So what about carbon? How many bonds can carbon make? Well, let's find carbon on the periodic table. Here it is. Here's carbon. So you count backwards from row 8 or column 8. 1, 2, 3, 4. So carbon can make 4 bonds. Now, what about chlorine? Let's find chlorine again. We were just working with it. And chlorine, remember, is right under the F, which is only 1 column away from the column 8. So chlorine can only make 1 bond. Now, what about neon? Neon is abbreviated Ne, and here's neon right here. Neon is in column 8. So how do you count backwards from the column that you're already in? Aha! See, neon already has its 8 electrons in its valence shell. It's full. It is full. Full up, no vacancy. There are no spaces to add any more electrons to neon's valence shell. And all of column 8 has a full valence shell, just like that. See, if you look at this, everything in column 8 is going to have 8 electrons in its valence shell because of the column number rule. So it doesn't have any room to make any new bonds. So these elements in column 8 never interact with anything else. They don't ever form covalent bonds with anybody because they're all full up with their own 8 valence electrons. And so that is why column 8 elements are called noble gases. And actually, the name noble gases, the reason why they were named that, well, one, because they're all gases, but the reason why they called them noble gases, because it actually started out as a joke among scientists about how snooty nobility people were, about how snooty royalty was. And so they were just making fun of royalty being snotty, calling these column 8A elements noble gases because they're too snotty to bond with any of the other element. They don't interact with anybody else. They're too snotty. So it started out as a joke among scientists calling them noble gases, just making fun of nobility who sticks their nose up at everybody else.
And your time is up, Professor DJ.
Good. I was finished anyway.
Okay, so just real quick, just to recap on bonding, for both ionic and covalent bonding, we are only talking about the valence shell electrons. Whatever other electrons are in the orbitals closer to the nucleus do not matter. It does not matter. You could have 2 electrons, you could have 1 million electrons closer to the nucleus, but we are only concerned with those 1 to 8 electrons in the valence shell of each of these elements. That's where all the activity takes place in chemistry. So you don't need to worry about how many electrons an element has. You only need to worry about how many valence electrons an element has. And as we saw in the periodic table, you can see how many valence electrons an element has by looking at which column it's in. And every element in that column from top to bottom has the same amount of valence electrons. And valence electrons is only 1 to 8 electrons. There are no more, there's not 0 electrons in a valence shell because then that wouldn't be the valence shell, the one underneath it would be. There's not 9 electrons in the valence shell because then a new outside shell would be created for that new electron, that extra electron. So there's only 1 to 8 electrons in the valence shell, and those 1 to 8 electrons are the only ones you need to concern yourself with in basic chemistry at all. So I bet that is a huge relief and a load off worrying about it. You only need to worry about that valence shell, and you only need to worry about the electrons in the valence shell. And those electrons, there's only going to be 1, 2, 3, 4, 5, 6, 7, or 8 of them, and that's it. Also, in both ionic and covalent bonding, either one, column 8, the noble gases don't bond with anyone because they are all filled up. They don't have any charge, they don't turn into ions because they don't lose or gain any electrons, and their valence shell is full with the top amount, the 8 electrons, so they don't have any electrons to want to share with anybody, and they don't need to borrow any electrons from anybody else, so they just kind of stay off by themselves, which is why they're called noble gases, because it started out as a joke, making fun of royalty being too snotty to run around with the commoners, so to speak, to make friends with the commoners and bond with them. So the noble gases don't bond with anyone, the very right-hand side of the periodic table in column 8. Okay, so for the differences between ionic and covalent bonds, ionic bonds are for, guess what, ions only. And ions are a special kind of form of the element where they've lost or gained electrons, and so now they have a positive or a negative charge. A metal ion on the very left of the periodic table loses electrons, so they have a positive charge. A nonmetal ion on the right-hand side of the periodic table gains electrons, so they have a negative charge, and these are ions. So ionic bonding is only between ions, the ones who have gained and lost electrons and so now have a charge. That's the only time ionic bonding is relevant. In ionic bonding, after all is said and done, once they bond together, they should be able to shift off their extra electron or get the electron that they need. So the total charge of the bond, the molecule, should total 0 charge. Everything should be back to balance, which means a 0 charge. And the positive charged ions are from the metals column on the very left. And you can tell what number of charge it is, how much of a charge it is, by its column number. The negative charge the negative charged ions are the nonmetals on the very right-hand side of the periodic table. And you can tell what their negative charge is if you count backwards from the end column, from column number 8, from the very last column, count backwards, and that's how many negative charges that ion is going to have in the nonmetal section. Okay, now for covalent bonds, these are for non-ions. These are for regular old elements, not the ones who have lost or gained electrons or have any charges. These are the regular elements that are already at a 0 charge. And covalent bonds only happen between nonmetals. That very right-hand block in the periodic table, like I called it, the metals is and the nonmetals are the 2 towers. So it's only the right tower on the very right-hand side of the periodic table. Those are the only ones that do covalent bonding. So you're not dealing with all the elements on the entire periodic table. You're only dealing with the elements in the nonmetal section. And I always think covalent cooperate. So they share the electrons by bonding. And one bond equals 2 electrons because each one puts in 1 electron for the bond. So if you have 2 elements bonded together, each element put in one valence electron for that bond. And so if you see 2 elements bonded together, that bond is going to equal 2 electrons, one from each element. The goal of covalent bonding is to bond to the different elements to get enough bonds so you can technically count 8 total valence electrons in your orbit, orbiting around you. And that's if including the electron that's donated from the other elements in that bond. So if you have one element that is bonded to another element, it picks up that extra electron from the bond that was donated from the other element. Now, the goal is to get 8 valence electrons in your valence shell, but your original number of valence electrons before you bond to stuff to get 8, the original number that you start out with is the exact same number as the column number that nonmetal element is in. So you just have to look up on the periodic table then where that nonmetal element is, look up and see what number column it's in, and that number is how many valence electrons that element has, that nonmetal element has. The number of bonds that each element needs to make to get up to 8 valence electrons is the same number as if you were to count backwards from the last column, from column 8. If you count backwards from column 8, however many columns you have to count back to get to the element in question, that is how many bonds that element needs to make in order to have a full set of 8 valence electrons. And if you notice on both ionic and covalent bonding, in ions, if you want to find out a nonmetal's negative charge, if the nonmetal is an ion, you count backwards from column 8, and that's how much of a charge that nonmetal ion has. That's how many extra electrons it has picked up. You can also count backwards from column 8 to find out how many bonds a regular element, a non-ion element, needs to make in order to get 8 valence electrons for the covalent bonding. So yes, these two are the exact same procedure. This is where you're doing the same thing, but it's for two totally different purposes. And one is we're talking about ions, what their charge is, how many extra electrons they have, and what their charge is. But for covalent, for regular elements that are not ions, you do the same thing. You count backwards from column 8, but that's to tell you how many bonds it needs to make in order to get that full set of 8 valence electrons in its outer orbital, in its valence shell.
That's the atom. That's it, man.
So that's the recap, and we have one more video after this about the secrets of the periodic table. These were the most involved videos, these videos 2 and 3. The first video was a refresher on the atom. Videos 2 and 3, this one's the third one, is about bonding. And this next video coming up, video 4, the final video, is just going to be some fun facts about the size of an atom, how to tell the size of an atom, how to tell its electromagnetism by reading the periodic table. It's just a bunch of bullet points on other secrets of the periodic table. But as I said, they're not as involved as these past two videos have been. If you made it through these past two videos, give yourself a pat on the back. This is as involved as the series is going to get.
You got it, man. You get an A.